Hello, and welcome to our first lecture on systems engineering. In this lecture, we're going to look at why companies need to use a systems engineering approach. My name is Tim Kerby, and I'm the CEO of Edinburgh Systems Ltd, a small company specialising in applying systems engineering and product management techniques to technology projects. So first of all, I'd like to tell you a little bit about our company. We specialise in the application of systems engineering and product management, and we teach large technology companies how to do this and how to improve their engineering practices. So that's building the capability within their organizations, it's training, coaching, mentoring, and it's actually doing some of the hands-on systems engineering and product development on actual real-life projects. Our key areas are semiconductor, electronics, and software industries, although we've worked across a wide variety of technology projects in automotive, medical, industrial, and many other sectors. One of our focus areas in particular is functional safety, as systems approaches are vital to ensure the safety of product development. So to start with, we're going to talk a little about systems engineering, what it is, and why we need that. So some definitions. What is a system? We can start right at the beginning that an atom is a system of subatomic particles. We don't have much influence over that as systems engineers, but we use those building blocks to build components. We can look at a transistor as a system of atoms, electronic component as a system of transistors. As we move up and build these into a circuit, we could say have a vehicle controller as a system of those electronic components. That's part of a car, a much larger system of different controllers, mechanical components, and other aspects. And that car forms part of the transport network, a system of vehicles all serving different purposes. And those systems, like the transport network, are part of a societal system, a system of people and the various different networks that provide us with the things that we need in life. So ultimately, everything is a system, and whether that's a small system, a small component, or a large system, whether that's a simple system or a complex system, we can apply systems engineering to all of these systems. So what is systems engineering? Systems engineering, the official definition is it's an interdisciplinary approach governing the total technical and managerial effort required to transform a set of customer needs, expectations, and constraints into a solution and to support that solution throughout its life. Now, that's a bit of a mouthful. What we say to people is systems engineering is really a methodology to do good engineering and build the right product for the market and build the product right first time by managing the complexity within that product development. So systems engineering here, it's used in a whole variety of things from aircraft, vehicles, electronic components. There's systems engineering has been utilized to build many of the products that you see today. To look at why we want to use systems engineering, we first need to think about what goes wrong within organizations and within product developments, and what causes that, and how those costs affect the return on investment in the product development lifecycle. First of all, we want to look at why products fail. And those products, when they're developed as a project, typically the causes are a lack of understanding of customer and stakeholder needs. So this data comes from a group called the Standish Group, who publish a report known as the Chaos Report, and this was the 2011 version. And you can see the top 3 reasons for projects failing: lack of user input, incomplete requirements, and changing requirements. All really a lack of understanding of those stakeholder needs. That also has an impact in terms of the unrealistic expectations, unclear objectives, and unrealistic timeframes, because if you don't know what you're designing, you can't really estimate your project appropriately. So all in all, that's a large proportion of project failures are down to not really understanding what you're meant to be doing with that project and why you need that project in the first place. And if we take that to product failure itself, it's, as we've said, the big cause is in building the wrong product for the market, is not understanding those needs, potentially bottom-up design, where you design something that the engineers want to build rather than something that the customers need, and potentially not looking at all the different stakeholders or prioritizing those requirements appropriately. Alternatively, you might build the product wrong, and that can be very expensive rework, which can mean you miss the slot for getting your product into the market. It can mean product recalls, which I have had to deal with in my career, and that can be a very expensive and very difficult situation with your customers. It can be, within this, often a failure to manage the interfaces between different components within your product and the external interfaces, poor agreement on what to build, and a lack of verification and validation. So you ultimately build something that isn't quite the right product for what your customer wanted, even though you may think it is. So you either didn't understand the problem or you didn't apply systems engineering techniques. And these are the two really big causes that we see across so many different companies in different industries, whether that's actual product design or even service design as well. This is a very common set of problems. So failure is very expensive, and we can look here. This is a chart from the International Council on Systems Engineering, a Systems Engineering Handbook. And upfront, when you start doing the system design at a concept stage, you're committing about 70% of the overall project costs very early on, because you're making those big decisions in your engineering that have an impact throughout the design, the development, the production and test, and ultimately the operation of that product in the market. So you want to make sure that you make those decisions correctly. And before you have something physical in your hands, it's a lot easier to change your mind on things. It's a lot cheaper to change your mind, because the cost of extracting those defects and fixing things goes up as we progress in the design life cycle. So at design stage, it's maybe 3 to 6 times. As we go into the development stage, it's 20 to 100 times. Once it goes into production and test, you're looking at maybe 1,000 times more expensive to be able to fix something that you could have fixed cheaply early on. So we want to get that right. And looking at the various studies out there, they say somewhere between 15 and 20% of your project's time and your project's cost should be spent in those upfront concept stages, doing that systems engineering and making sure you get things right. And that's what we call pre-work, not rework. So it's doing that upfront pre-work to avoid the rework later on. So systems engineering as a discipline can't stand alone. You need an organization that supports that discipline and supports the systems engineers. One thing I see a lot in industry is companies have a small number of systems engineers, or they're starting to recruit them, often because they have started to do functional safety and safety products, particularly in the automotive industry. And the organization isn't always set up in the best way to make good use of the systems engineers and create the right culture and environment for them to succeed. So this is a framework here that I have often applied within the organizations to help them with their product development life cycles and how they can structure their developments to get the best out of their product development life cycle and their engineering. So first thing, at the top level, we're generating knowledge from the market. This is part of that 18% of the time. So we start by looking at the company vision, where that company wants to go, and what that company is good at. So what their distinctive competence is, where their skills are. Using that as a guide, we start to understand the market, identify the stakeholders, and prioritize and value those market problems so that we're building the things that actually have value for the customers. Then, and again in that 18%, we start to define and refine the requirements and some product concepts that may meet those requirements, and look at what we want to start building. And we then take that through architecture, building the product, and selling the product. And all along the way, we're verifying and validating to make sure that that is still the right product, that the customers haven't changed anything, and it's still the right product for the market and meeting those needs. We also need to consider at the bottom is technology development, and it's making sure that new technologies are actually technologies that are going to have future market value. So thinking about things early that you might need, prioritizing your R&D spend accordingly, and looking at your technology readiness. It's also building some of the standard IPs, some of the boring things potentially, that are going to be reused across a lot of projects, and building them in the right way, making sure they're well documented, easily reusable, composable, so they have standardized interfaces, you can drop things in. It's block-based approaches here. So we can look at where this goes wrong in the organization as well. And first of all, a lot of companies think they can do anything. They start building things that they don't have the skills to do. The next is they focus only on their key customers, or they don't elicit the right problems. They ask customers for specifications and data. They don't understand why they need to solve these problems and what products their customers are building. And if you're only working with your key customer, you're cutting out a lot of the market because there's potentially a lot of other people who have different needs, and you should be speaking to those people as well. That ultimately means you can be solving the wrong problem, and the companies who are often spend too little time on the requirements, and they don't iterate. So they don't take these concepts back, take those early ideas back to their customers. They just go off and they iterate internally, developing the things that they feel are important without going back and checking these with the market. This is often the evolution of a single concept rather than considering one or two different potential solutions and trading off the pros and cons of each of them to make the right engineering decisions. They often forget the validation, or they don't validate against requirements, they validate against internal specifications and standards. Or in this bottom stage, they're not linking that R&D to strategic needs, so not linking the R&D to the market, and that can result in companies behaving like universities, so the R&D can be very uncontrolled in what is interesting to the engineers, or it could be too little and too late. If you're not focusing on that, on the areas that are important, you might find that there's something critical for a project that then becomes critical path and holds up the development. And the final one, and perhaps the most important here, is a failure to learn and evolve. So too many organizations, and some of those that I've worked with, you can go in and you can speak to the engineering staff and say, can you tell me how successful the last product you worked on was? What's the market share? How many have sold? Is it a good return on investment for the organization? Too many of them, sadly, have no idea. They don't know what the customers liked, what they didn't like, and they don't use this information to evolve for future product developments. They've had their celebration as soon as that product hits the market, and they've moved on to the next thing. And that's critical to making sure that your products are successful in the future. So, to summarize, everything's a system. We can apply systems engineering techniques to all levels and all sizes of systems. Products often fail due to the poor understanding of requirements. It's critical to get those requirements right. Systems engineering helps us build the right products right, so that's understanding the needs and market value to build the right products, and the upfront work to reduce the risk of errors and rework, so 15 to 20% of your time and budget to make sure you're building that product right. And your systems approaches may require some organizational change, often considering the organization as a system itself. For those successful products, that's making sure you have the right roles, responsibilities, competence, your tools, templates, and techniques, and some of your organizational environment and culture to make sure that your systems engineers thrive and succeed. If you've got any questions, please get in touch. My email address is here, and I would love to hear from you. Thank you.